Hi everyone, this is Dr. GVR Seshagiri Rao, Professor in the Department of Mechanical Engineering, Institute of Aeronautical Engineering, Hyderabad. So we are discussing about solid mechanics and material subject. So already we have discussed about all topics. Theory part is completed. So we have discussed about simple stresses and strains and the theory of simple bending and shear force and bending moment diagrams and columns and studs. All theory related parties we have discussed. Now we will discuss about problem solving. So how to solve the problems based on based on formulas and then derived equations. We will see today simple stresses and strains problems. So already we have discussed about simple stresses, types of stresses and strains, and then how to solve problem by using different equations. In today's session I will explain. So first of all, you should know about the course outcome. The student should be able to explain the concepts of stress strain relationship, material constitutional relationship, and strain energy induced in linear or elastic, homogeneous, and isotopic materials subjected to force. So, whenever the component is subjected to load, the force, so how much strain energy induced and how much stress induced, and what is the relationship between stress and strain. After completion of this topic, the student can able to answer. So the problem solving on simple stress and strains, the introduction part is, so once again recall the stresses and strains, whatever you have learned in previous sessions. When an external force acts on a body, the body tends to undergo some deformation. So due to cohesion between the molecules, the body resists deformation. So whenever the external force acts on a body, the body tends to undergo some deformation already you know. So due to the cohesion property between the molecules, the body resists deformation. So this resistance by which material of the body opposes the deformation is known as strength of material. So the beyond the elastic stage, the resistance offered by the material is less than the applied load. In such case, the deformation continues until failure takes place. Already we have seen in a stress strain diagram. You know, in a stress strain diagram, stress and strain. So in this, up to elastic limit, there is no problem. There is no deformation, and then entrance in the entrance, the lower yield point and upper yield point, and then fracture. So this is ultimate stress and then failure point, and upper yield point and lower yield point. So this is elastic limit stage. So within elastic stage, resisting force equals to applied load. So whatever applied load, the resistance deformation is equal. This resisting force for unit area is called stress or intensity of stress. So you know the Hooke's law, the stress is directly proportional to strain. So you can write stress is equal to, with the help of Young's modulus, E into epsilon. Okay. Now stress already we have discussed, and stress is equal to load per area, and strain is equal to the change in length by original length. That is deformation, how much deformed. So now we will see how to solve the problem based on this simple stress and strains relations. The problem 1, a rod 150 centimeters long of diameter 2 centimeter is subjected to an axial pull of 20 kilonewtons. So if the modulus of velocity of the material of the rod is 2 into 10 to the power of 5 Newton per mm square. So the stress, find out determine the stress and then strain and then elongation of the rod. So first of all, for any problem, the given data you should write. So here the given data, the given what is given 150 centimeters long rod, length is equal to 150 centimeter, and then diameter is 2 centimeter, subject to an axial pull of 20 kilonewtons. The load is 20 kilonewtons. The modulus of velocity of the material of the rod is given E is 2 into 10 to the power of 5 Newton per mm square. So what he has asked, determine the stress, strain and elongation of the rod. So apply relations. So first convert into mm. So centimeter 150 centimeter convert into mm, multiply with 10. So 1500 mm and 20 mm. At 20 kilonewtons, converting 20 into 10 cube newtons, and already this elasticity of the material of the rod is 2 into 10 to the power of 5 Newton per mm square. So first stress is equal to sigma is equal to load per area. What is the load given here? 20 kilonewtons. So right, 20 kilonewtons, 20 10 to the power of cube newtons by area. So what is the area of the rod? You should calculate 5 by 4 into d square. So diameter of the rod given, it is a circular shape. So that find out diameter 20 square. So calculate area in mm square you will get. And then substitute this area in this stress relation, you will get stress. Similarly, strain is equal to delta L by L. But elongation, you don't know. So how do you calculate the strain? You know that Hooke's law relationship, stress is directly proportional to strain. So stress is directly proportional to strain. Stress is equal to E into epsilon. So that strain is equal to stress upon Young's modulus. Stress already you have calculated. So substitute in this relation, you will get a strain. And third one is the elongation, delta L. So delta L is equal to strain multiplied with L. Since the strain is equal to delta L by L. Clear? So now the solution here given. So 150 centimeters and the diameter is 2 centimeter convert into mm. So already I told you. So the area is 105 mm square. And modulus of velocity also given 2 into 10 to the power 5 Newton per mm square. Now stress calculation is you will get 63.662 Newton per mm square. Using equation already you have studied in we have discussed in the theory part. The strain is obtained as E is equal to sigma by E. The strain epsilon is equal to RE is sigma by E. The strain you will get the elongation dl or delta L by L. So the elongation delta L is equal to E into L. So you will get 0.0477 cm. So like this, how to solve this problem by using the simple equations. Next, we will see the second problem, model 2. Find the Young's modulus of a brass rod of diameter 25 mm and of length 250 mm. So in this problem, he has not given the Young's modulus. Need to calculate. And subject to a tensile load of 50 kilonewtons. When the extension of the rod is equal to 0.3, extension also given 0.3 mm. So now write down the given data. What he has given. Diameter of the rod is 25, length is 250. 25 mm, directly given in mm. Length is 250. 250 mm. Subject to a tensile load of 50 kilonewtons. And then the extension of the rod is equal to 0.3 delta L, the change in length. So now converting to newtons, 50 into 10 cube newtons. So what he has asked? Find the Young's modulus. For Young's modulus, sigma is equal to E into strain. As per Hooke's law, according to the Hooke's law, the stress is directly proportional to strain. So Young's modulus is E is equal to sigma by strain. So what is sigma? Stress. How do you calculate stress? Stress is equal to load per area. Per area, we don't know. Calculate area. Area is 5 by 4d square. So diameter is given 5 by 4 into diameter 25 mm. So 25 whole square. So you will get area and then substitute in this sigma you will get. Strain is equal to delta L by L. So already delta L given and L also given. So that change in length by original length delta L by L. So I will get strain and then substitute these two values in this equation, you will get E. So here shown the detailed solution here. The D is diameter 25 mm. The area of the rod is 5 by 4 into 25 whole square. The tensile load is 50 kilonewtons. So the extension of the rod is DL is 0.3. The length of the rod is 250 mm. So the stress is equal to load per area. Load is 50,000, 50 into 10 cube newtons, and then area is 5/400 d square. Calculate, you will get 490.87 mm square. The strain is delta L by L. So that is 0.3 dl by 250. So already given delta L 0.3 mm, delta L or dl. So now Young's modulus is obtained. E is equal to stress upon strain. So we will get answer in Newton per meter square, convert into Newton per mm square. 1 Newton per mm square is equal to 10 to the power of 6 Newton per meter square, and then again convert into giganewton per meter square. So finally we will get 84.883 giganewton per meter square. This is another approach for calculating Young's modulus. Next, problem 3. Here, the tensile stress was conducted on a mild steel bar by using universal testing machine UTM. The following data was obtained, recorded from the test. One is diameter of the steel bar 3 cm, gauge length of the bar 20 cm. The given data and the load at elastic limit 250 kilonewtons, and then extension at a load of 150 kilonewtons. So the load at elastic limit is 250 kilonewtons, and then extension of load at 150 kilonewtons 0.21. So the maximum load is 380. So total extension is 60 mm. So diameter of the rod at the failure 2.25 centimeter. So what he has asked, determine the Young's modulus. E, the stress at elastic limit, and then percentage elongation. The percentage decrease in area. The percentage decrease in area and the percentage elongation. The percentage in delta L. The percentage decrease in area delta A. So first of all, need to write the given data and then calculate the area and stress at different loads. So already you know the area 5/4 into d square, and then stress load per area, strain delta L by L, and E sigma by epsilon. So these are the relations. Now here the diameter of the steel bar 3 centimeter, and then the diameter of the rod at the failure is 2.25 centimeters. We need to calculate separately at the diameters and then calculate stress at corresponding loads. So here shown the area of the rod. Here area of the rod is 5/4 into d square, already you know. Calculate, d already given. And later you can convert into meter square. Just to find the Young's modulus, first calculate the value of stress and strain within the elastic limit. So the load at elastic limit is not given, but a load of 150 kilonewtons which is within the elastic limit given. The corresponding extension is at 150 kilonewtons. The extension is, corresponding extension is 0.21 mm. Okay. Next, hence, these values are used for stress and strain within the elastic limit. First, calculate stress, load 150 kilonewtons, and area at this 150 newtons, the diameter is 3 centimeter. So that whatever you calculated, this value substitute in this. Strain is equal to increase in length or extension by original length. So increase in length or extension 0.21 by original length or gauge length is 20 into 10 mm. So now Young's modulus is E is equal to stress upon strain. So now the Young's modulus calculated and converted into giga. And then the stress at the elastic limit is given by stress is equal to load at elastic limit upon area, and then calculate, you will get 353.68 meganewton per meter square. So the percentage elongation is obtained as, so what he has given in the problem. So what he has asked, Young's modulus is asked, stress at the elastic limit is over, the percentage elongation and percentage decrease in area. So the percentage elongation is obtained as percentage elongation, total increase in length upon original length. So that is called as gauge length. What is the original length of the rod? So total increase in length is 60 mm by original length is 20. So convert into mm. So we will get 20 into 10 and then 60 by 20 into 10 into 100, 30%. So this is percentage elongation. So the original length is, the length of the rod is given, the gauge length of the body is 20 cm. So that's why convert into mm, 20 multiplied with 10, you will get in mm. So the percentage decrease in area, the percentage decrease in area is original area minus area at the failure by original area. So the original area is 5 by 4 into diameter 3 centimeter square, area at the failure. So at the failure, the diameter is 2.25. So calculate this difference, you will get percentage decrease in area. So what is the original area? A1. And after decreasing diameter, the 5 by, what is the area here? 5 by 4 into the original area, 5 by 4 into d1 square. After reduction, A2 is 5 by 4 into d2 square. So we'll get the percentage decrease in area. Clear? So like this, to calculate by using simple stress and strains relations, according to the given data. So these are the references I have taken. S. Ramamurthy. The title of the book is Strength of Material. And R.K. Bansal, textbook of Strength of Material. And R.S. Kurmi, that is Strength of Material textbook name, and then publishers are Richard and Co. New Delhi. So refer any one textbook for other more information. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.